Voyager has been travelling through space for decades, crossing beyond the planets and into interstellar space, where it passed through regions of extreme particle density and intense energetic conditions. Now, reports link to its data point toward a 50,000-degree wall at the edge of the solar system. But what does that actually mean, and what is really happening at this boundary between the Sun's influence and interstellar space? Stay tuned. The signal from nothing. You see, Voyager 1 is still talking, but the way it talks now is almost strange when you think about how far it has gone. Because the signal that reaches Earth today started its journey more than 15 billion miles away, and by the time it arrives, it is so weak that it has to be pulled out of background noise using some of the most sensitive deep space antennas on Earth, and yet it still carries information that no other spacecraft has ever been able to send back. Information from a place no human object had ever reached before, a region where the Sun is no longer the dominant force, and where space itself starts to behave differently in ways that were not fully expected when Voyager was launched. The idea that a machine built in the 1970s is still operating today feels almost unreal when you break it down properly, because Voyager was never designed to survive this long or travel this far. It was designed for a short mission to visit Jupiter and Saturn, take close images, measure magnetic fields, and send back data for a few years before slowly shutting down. But instead, it kept going, powered by systems that were never meant for long-term survival in deep space. And as it moved further and further away from the Sun, it crossed regions no spacecraft had ever entered, not once, not even close, until it finally reached a point where the Sun's influence weakens so much that space starts reacting more to the galaxy around it than to our own star. What makes Voyager's signal even more important is not just the distance or the age of the spacecraft, but what it recorded while crossing into that outer region. Because the instruments on board did not just show a smooth fading of solar influence, instead they recorded sudden and sharp changes in the environment, almost like the spacecraft had entered a different layer of space where conditions changed faster than expected. And these changes came in the form of a plasma density spike, where the number of charged particles around the spacecraft increased suddenly, even though the region was supposed to be thinning out, an energetic particle shift, where particles started moving with higher energy levels than before, and a magnetic field distortion, where the direction and strength of magnetic fields shifted in ways that did not match earlier models of that region of space. These readings were not small variations. They were strong enough to make scientists stop and look again at what Voyager was telling them, because it suggested that the boundary of the solar system was not a calm and gradual fade into interstellar space, but instead a region of active interaction, where the solar wind coming from the Sun was colliding with the interstellar medium outside our system in a way that created turbulence, compression, and sudden changes in particle behavior. And this is where the idea of a violent transition zone begins to form, not as a physical wall in space, but as a region where two different environments are pressing against each other with enough force to create sharp and unexpected changes in data readings. When people hear about a wall at the edge of the solar system, it often comes from how dramatic these readings appear when simplified, because the spacecraft does not pass through a smooth gradient. Instead, it experiences jumps in values that look like sudden boundaries, especially in plasma data, where density can rise sharply in a short period of time. And this creates the impression that Voyager has hit something solid or structured, even though what is actually happening is far more complex, because space at that distance is not empty in the way most people imagine. It is filled with extremely thin plasma, magnetic fields stretching across huge distances, and energetic particles moving at high speeds, all interacting in a region where the Sun's outward pressure is finally meeting the pressure of the galaxy itself. To understand why Voyager was even able to reach this region, it is important to go back to what it actually is and why it exists in the first place, because Voyager 1 and Voyager 2 were launched in 1977, during a rare planetary alignment that allowed spacecraft to use gravity assist to travel from one outer planet to another without needing massive amounts of fuel. And this alignment meant that a single spacecraft could be slingshotted by Jupiter's gravity, then Saturn's gravity, and potentially continue outward into deeper space, something that had never been attempted at that scale before. And at the time, the main goal was simple and focused, which was to study the outer planets up close, take images of their moons, measure their atmospheres, and send back data that could only be collected during a brief window when such an alignment was possible. The design of Voyager was based on that short mission idea, not long-term survival, which makes its current operation even more surprising, because the spacecraft carries a power system called a radioisotope thermoelectric generator, or RTG, which produces electricity from the natural decay of plutonium, and this system slowly loses power over time, meaning that every year Voyager has less energy available to run its instruments and transmit data. Yet despite this limitation, it continues to operate critical systems and send back measurements from a region of space no other probe has ever reached directly, and that alone makes it one of the most important scientific instruments ever built for studying the outer boundary of our solar system. Communication with Voyager is also extremely slow and extremely weak, because the signal takes over 20 hours to travel one way between Earth and the spacecraft, meaning that any command sent to Voyager takes almost 2 full days to get a response. And by the time data arrives, it has already been travelling through space for nearly a full day, weakening as it spreads across distance, which means scientists must carefully plan every interaction with the spacecraft without real-time control, relying instead on pre-programmed instructions and extremely precise calculations, since even a small error in timing or signal interpretation could mean losing valuable data from a region that cannot be reached again by any current mission. Despite these challenges, Voyager still carries a small set of working scientific instruments that continue to provide direct measurements from interstellar space, including the plasma science experiment on Voyager 2, which measures charged particles in space and helps determine how dense the surrounding environment is, the cosmic ray subsystem, which tracks high-energy particles coming from outside the solar system and even from distant parts of the galaxy, and the magnetometer, which measures magnetic fields and how they change as the spacecraft moves through different regions, and together these instruments form a simple but powerful system that allows scientists to map the invisible structure of space far beyond the planets. What makes Voyager especially unique is that it is still the only human-made object that has directly entered interstellar space and sent back data from it, meaning no other spacecraft has physically crossed the same boundary and remained active long enough to study it in detail. So every reading it sends is a first-time measurement for humanity, and this is why even small changes in its data, such as sudden particle spikes or magnetic shifts, are treated as extremely important clues, because they are revealing what happens when the solar system's influence finally gives way to the wider galaxy. As Voyager moves further away, it is not entering empty space in the simple sense, but instead passing through a region where the solar wind, which is a constant flow of charged particles from the Sun, slowly loses its strength and begins to interact more strongly with the interstellar medium, which is the very thin mixture of gas, dust, and charged particles that exists between stars. And when these two flows meet, they do not cancel each other smoothly. Instead, they create a complex boundary region where pressure builds, waves form, particles accelerate, and magnetic fields twist and adjust in response to competing forces. And this is the region where Voyager detected those sudden changes that were later described in simplified terms as extreme temperature spikes, or even as a wall in some public reports. The reason temperature readings in this region appear so extreme is because temperature in plasma does not work the same way it does in air or on Earth, since it is not about how hot something feels, but about how fast individual particles are moving. And in very low density space, a small number of particles can carry extremely high energy, which leads to readings that appear like tens of thousands or even hundreds of thousands of degrees, even though there is almost no matter there to transfer that heat in any meaningful way. So the spacecraft is not passing through something that would burn or heat it in a traditional sense, but instead passing through a region where particle energy levels are unusually high compared to surrounding space. The structure of the solar system, where the edge really is. The solar system is often shown in simple diagrams where the sun sits in the middle and everything else spreads out around it in neat circles. But that picture does not match what space actually looks like when you move far enough away from the planets. Because the sun is not just sitting in empty space with planets around it, it is constantly throwing out a stream of charged particles in every direction. And this stream is strong enough to push against the space between stars, shaping a huge invisible region around the entire solar system that changes how everything behaves far beyond the orbit of Neptune. And this is where the real structure of the solar system begins to look very different from the simple models most people see. Close to the Sun, everything feels more familiar in terms of how space behaves, because the inner planets, Mercury, Venus, Earth and Mars, move inside a region where sunlight is strong, and the solar wind is still powerful enough to fill space with charged particles that move outward at high speed. And even though space between planets looks empty, it is actually filled with this constant outward flow that comes from the Sun's outer atmosphere, meaning that every planet is always inside a moving river of particles that stretches far beyond what we normally think of as the edge of the solar system. And this flow does not stop suddenly at any planet. It continues outward in a weakening but still active stream that eventually reaches much farther than Pluto and the outer planets. Past the inner planets, there is the asteroid belt, which is a wide region filled with small rocky bodies that never formed into a planet. And while this region is often shown as crowded in diagrams, in reality, the space between asteroids is enormous, but it still represents a transition zone in the structure of the solar system, because it marks the area where the Sun's gravity is still dominant, but the material left over from planet formation is no longer forming large bodies, and even here the solar wind is still strong enough to influence particle behavior and carry energy outward, shaping how dust and small particles move through space. Farther out, the gas giants appear: Jupiter, Saturn, Uranus and Neptune, and these planets dominate their local regions with strong gravity fields and complex magnetic environments, especially Jupiter, which has such a strong magnetic field that it creates its own miniature particle system around it, trapping charged particles and forming radiation belts that are far more intense than anything near Earth. And this is important because it shows that even before reaching the outer boundary of the solar system, space is already filled with overlapping magnetic and particle systems that interact with the solar wind in different ways, depending on distance and location, meaning there is no single uniform environment even inside the planetary region. Beyond Neptune, the structure becomes less familiar and much more spread out, and this is where the Kuiper Belt begins, a vast region filled with icy bodies, dwarf planets, and remnants from the early formation of the solar system. And while it is often described as a belt, it is not a dense ring, but a wide and thin distribution of objects that extend far into space. And this region marks the last major population of solid bodies that still belong clearly to the solar system. But even here, the Sun's influence is still present in the form of gravity and the solar wind, which continues pushing outward far beyond these distant objects, carrying energy and charged particles into space that is no longer dominated by visible planetary systems. The real outer structure of the solar system does not follow the shape of these object-based regions, because once you move beyond the Kuiper Belt, the main structure is no longer defined by planets or rocks, but by invisible flows of particles and magnetic fields. And this is where the solar wind sphere begins, also called the heliosphere, which is not a physical shell, but a huge bubble-like region formed by the outward pressure of the solar wind pushing against the thin gas and particles that exist between stars. And this bubble is not fixed or smooth. It changes shape depending on solar activity and how the solar wind interacts with the surrounding interstellar medium, meaning that the edge of this region is constantly shifting rather than sitting still in space. Inside the heliosphere, The solar wind travels outward at high speed, carrying magnetic fields from the Sun along with it, and this creates a large-scale structure where the Sun's magnetic influence stretches far beyond the planets, shaping how charged particles move and how radiation behaves. But as this flow moves farther from the Sun, it begins to slow down because it eventually encounters pressure from the interstellar medium, which is the very thin mixture of gas and charged particles that exists between stars in the galaxy. And this meeting point is not smooth, because two different streams of particles are colliding at extremely low densities over vast distances. And instead of blending evenly, they create shock regions where speed, density, and energy change rapidly. The first major transition in this outer region is called the termination shock, and this is the point where the solar wind, which has been moving outward at very high speed, suddenly slows down because it starts to feel the pressure of the interstellar medium pushing back against it, and when this happens, the energy of the particles does not disappear. Instead, it gets converted into heat and motion within the plasma itself, causing particles to become more energetic and more chaotic in their movement, even though the overall flow is slowing down. And this creates a region where readings suddenly shift in ways that are much sharper than expected, because instead of a gradual slowdown, the solar wind experiences a sudden change in behavior over a relatively short distance in space terms. After the termination shock, the solar wind does not stop, but it enters a much thicker and more turbulent region called the heliosheath, where the slowed down solar wind continues moving outward, but is now heavily mixed with particles from the interstellar medium. And this region is filled with constant disturbances, waves, and fluctuations in magnetic fields, because the solar wind is still trying to push outward while the surrounding space is pushing back. And this creates a kind of unstable environment where conditions change frequently over time, and where particles can gain or lose energy, depending on how local magnetic fields shift and interact. Meaning, this is not a calm boundary, but a highly active region of space where multiple forces are constantly competing. Inside the heliosheath, the environment becomes more complex because the solar wind is no longer the only dominant flow, and interstellar particles begin to enter the region more easily, mixing with solar particles and creating a blended environment where it becomes difficult to separate what belongs to the Sun's influence and what belongs to the galaxy outside. And this is where spacecraft like Voyager start to record sudden changes in data, because instead of moving through a steady environment, they are moving through a region where conditions can shift over relatively short distances, and where particle density can rise or fall unexpectedly, depending on local interactions between magnetic fields and particle flows. As the heliosheath extends outward, the solar wind gradually loses its ability to dominate space, and this leads to the heliopause, which is not a wall or a solid boundary, but a pressure balance region where the outward force of the solar wind becomes equal to the inward pressure of the interstellar medium. And this balance creates a kind of invisible surface that marks where the Sun's influence stops being the strongest force in that region of space, and instead the galaxy outside begins to take over as the dominant environment. But even this boundary is not sharp or fixed, because it changes depending on solar activity, meaning that at different times the heliopause can shift slightly inward or outward, depending on how strong the solar wind is at that moment. When spacecraft like Voyager move through this outer structure, they do not experience a single clear moment where everything changes at once. Instead, they pass through layers where conditions shift step by step, sometimes gradually and sometimes in sudden jumps, and this is what makes the data so complex, because one instrument might show a slow decline in solar particles while another shows a sudden increase in cosmic rays, and another might detect rapid changes in magnetic field direction, all happening within the same region of space, but not always at the same time or in the same way. And this creates a layered picture of the solar system's edge that is far more complicated than a simple boundary line. The heliosphere itself is not perfectly symmetrical because it is shaped by both the motion of the Sun through the galaxy and the varying pressure of the interstellar medium around it, which means that one side of the solar system may have a different boundary distance compared to another side, and this makes the outer structure more like a stretched and shifting bubble rather than a perfect sphere, with regions that expand or compress depending on how external forces push against it. And this asymmetry becomes important when interpreting data from Voyager 1 and Voyager 2, because each spacecraft travelled in a different direction and therefore experienced slightly different boundary conditions. Even after passing the heliopause, the environment does not become empty, because interstellar space itself contains plasma, magnetic fields, and cosmic radiation that continue to interact with any object moving through it. And this region is called the interstellar medium, which is not a uniform space, but a very thin and widespread mixture of particles that fill the space between star systems. And although the density is extremely low compared to anything near planets, the energy carried by these particles can still be high, especially when they come from distant cosmic sources or are influenced by galactic magnetic fields that stretch across large portions of the Milky Way. Inside this interstellar medium, the Sun's influence is still present, but much weaker, and it slowly fades as distance increases, but it never disappears completely in a sharp cutoff. Instead, it blends into the larger galactic environment in a gradual way, and this blending is what Voyager has been measuring as it continues moving outward, recording changes in particle density, magnetic field direction, and cosmic ray intensity, showing that even at the edge of the solar system, space is still active and structured, just in a way that is controlled more by the galaxy than by the Sun itself. The termination shock, first violent transition zone. Voyager 1 reached the termination shock in 2004 after moving for decades through space that was still dominated by the Sun's outward flow. And what it entered was not a quiet outer edge or a gentle fading of solar influence, but a sudden change in how space itself was behaving, because up to that point, the solar wind had been moving outward in a fast and steady stream, carrying charged particles away from the Sun in all directions, and this stream had been filling the entire region around the planets like a continuous outward breath from the Sun. But as Voyager moved farther away, that outward flow began to meet a very different environment that was not empty at all, but filled with extremely thin gas and charged particles that exist between stars. And this meeting point created a sharp physical reaction in the form of a shock region, where the behavior of particles changed in a very short distance compared to everything before it. The solar wind does not travel through space without resistance, because even though space looks empty, it contains particles and magnetic fields that are spread out over huge distances. And as the solar wind moves outward, it carries energy and pressure with it. But at a certain distance, that outward pressure becomes weak enough that it starts to feel the push from outside the solar system, and this is where the flow cannot continue at the same speed. So instead of slowing down gradually over a long smooth distance, it hits a region where the change happens quickly and strongly, and this is what forms the termination shock, a boundary that is not a physical wall, but behaves like one in terms of how sudden the change in conditions can be. When Voyager 1 crossed this region, the instruments recorded a very clear shift in particle behavior, because the solar wind, which had been moving at extremely high speeds for billions of miles, suddenly dropped in speed as it entered a region where the outward pressure of the Sun was no longer strong enough to maintain that fast flow. And this slowdown did not mean that the energy disappeared. Instead, the energy in the moving particles was transferred into random motion, which means the particles began to move in more chaotic and scattered ways rather than flowing in a steady direction. And this change caused a rise in what is measured as temperature in plasma physics, not because anything became hot in the normal sense, but because the particles themselves were moving more energetically in all directions after being slowed down by the surrounding medium. At the same time, the magnetic field carried by the solar wind began to react strongly to this slowdown, because magnetic fields in space are tied to the motion of charged particles. And when those particles change speed and direction suddenly, the magnetic field lines also become twisted and disturbed, which leads to what is described as magnetic turbulence, a condition where the field does not remain smooth or stable, but instead shifts and fluctuates as different streams of charged particles push and pull against each other in different directions, creating a highly unstable environment compared to the smoother flow closer to the Sun. This region also becomes important because it is not empty in the way space is often imagined, since even before Voyager reached it, there were already low-density particles present in the outer solar system and beyond. And when the solar wind reaches this region, it does not pass through cleanly, but begins to interact with those particles, transferring energy into them and creating new motion patterns that were not present before. And this interaction is what starts the process of particle acceleration, where charged particles gain energy from the collision between the outgoing solar wind and the incoming interstellar material, leading to a region where particles can reach much higher energy levels than expected based on distance alone. Instead of a smooth fading of solar influence, the termination shock becomes a place where energy is redistributed quickly across different forms, where the bulk motion of the solar wind slows down, but the random motion of particles increases, and where magnetic fields become disturbed rather than stable. And this combination creates a region that is physically active, even though it is far from any planet or direct sunlight, showing that the outer solar system is not a quiet space, but a region where large-scale flows of energy are still shaping the environment in noticeable ways. Beyond this transition zone lies the heliosheath, which is a much thicker and more extended region where the solar wind continues to move outward, but under very different conditions, because after passing through the termination shock, the solar wind no longer travels freely at high speed, but instead moves more slowly and becomes heavily mixed with particles from outside the solar system, creating a wide region filled with interaction between two different particle environments, one coming from the Sun and the other coming from interstellar space, and neither of them fully dominates, which leads to a constant state of mixing and disturbance. The heliosheath is not a smooth layer, but a highly active region filled with chaotic plasma behavior, where charged particles move in complex patterns, influenced by constantly changing magnetic fields. And as Voyager moves through this region, it records variations that do not remain stable for long periods of time, because the environment itself is constantly shifting as different streams of particles collide, merge, and separate, creating a structure that changes over both distance and time, meaning that conditions at one point are not exactly the same as conditions even a short distance away. Inside this region, shock waves appear frequently as different flows of particles meet and compress against each other, and these shocks are not like sound waves in air, but are instead changes in plasma pressure and magnetic field strength that move through space as disturbances in the charged particle environment. And when these shocks pass through an area, they temporarily increase the energy of particles in that region, causing sudden spikes in readings that can be detected by spacecraft instruments, which is why Voyager often records changes that appear sharp and sudden, even though the underlying process is continuous and spread out over large distances. Magnetic field distortion becomes a constant feature of this region because the solar wind is no longer a single uniform stream, but a mixture of many interacting flows. And as these flows interact with interstellar particles, the magnetic field lines become stretched, bent, and twisted in different directions, creating a complex structure that is not stable or uniform. And this makes the heliosheath one of the most difficult regions to model accurately, because the conditions change depending on both the distance from the Sun and the local interactions happening at any given moment. The temperature behavior in this region also becomes more complex, because as particles collide and interact, their energy levels increase in certain areas while decreasing in others, depending on how shocks and magnetic fields redistribute energy. And this leads to regions where particle energy appears to rise significantly, even though the overall density of matter remains extremely low, meaning that the concept of temperature here does not reflect heat in a traditional sense, but instead reflects the average energy of particles moving through space, which can vary greatly depending on local conditions and interactions. As Voyager continues moving through the heliosheath, it passes through regions where solar wind particles are still present, but are gradually losing their dominance, while interstellar particles become more noticeable and begin to mix more heavily into the environment. And this mixing does not happen evenly, because different streams of particles enter and interact at different angles and speeds, leading to uneven regions of density and energy that change depending on how the flows intersect at any given moment, creating a layered and shifting structure rather than a single uniform zone. Within this environment, energetic particle acceleration becomes more active, because when fast-moving solar particles collide with slower or differently directed interstellar particles, energy can be transferred in ways that increase the speed and energy of certain particles, leading to a population of highly energetic particles that can travel in different directions through space. And this process is not limited to a single location, but occurs throughout the heliosheath wherever conditions allow particle streams to interact strongly enough to exchange energy. Voyager's instruments detect these changes as shifts in particle counts and energy levels, which appear as sudden rises or drops depending on how local conditions change along its path. And these variations help build a picture of a region that is not static, but constantly shaped by movement and interaction, where no single measurement remains stable for long, because the environment itself is always in motion, even at distances where the Sun's influence is becoming weaker and the interstellar medium is becoming more noticeable. The heliosheath therefore becomes a wide transition zone, where the solar system is slowly handing over influence to the surrounding galaxy. But this handover is not smooth or direct. Instead, it is filled with overlapping flows, pressure changes, and magnetic interactions that create a complex and active environment. And Voyager moving through this region is effectively passing through a long corridor of changing physical conditions, where every shift in data reflects a different part of this ongoing interaction between the Sun's outward flow and the galaxy's incoming environment. The 50,000 degrees Celsius wall. Claim. What data actually shows. Voyager never crosses anything that behaves like a solid barrier, because there is no surface, no material layer, and no physical object sitting at the edge of the solar system that can be touched, hit, or pushed against. And what actually happens in the data is something very different from what the word wall suggests, because the spacecraft moves through space that is already filled with extremely thin plasma. And as it travels farther from the Sun, it enters regions where that plasma changes in speed, density, and energy in ways that can look sudden when measured over time, even though in reality the changes are spread out across huge distances that cannot be seen directly, but only measured through instruments that sample particle behavior. The most important point that comes directly from Voyager data is that there is no single moment where everything stops and a new environment begins in a clean and simple way. Because what the spacecraft records is a sequence of changes that happen in steps, where one type of particle flow weakens while another becomes stronger, and where magnetic fields shift direction gradually but sometimes with sharp local variations, and where particle counts rise or fall depending on how different streams of plasma interact at that exact region in space. And when these changes are plotted over time, they can appear as sudden jumps, which is where the confusion around the idea of a wall begins. One of the strongest signals recorded in this region is a sudden jump in plasma energy, where the particles surrounding the spacecraft begin to move with noticeably higher energy levels compared to the region just before it. And this does not mean that the environment becomes hot in the normal sense of heat that would burn or transfer warmth to an object, because in space at this distance, there are so few particles that even if each particle carries high energy, there are not enough collisions between them to transfer heat in the way it happens in air or water. Instead, what is being measured is the energy of individual particles moving at high speeds. And when those speeds increase or become more chaotic, the instruments register this as a rise in temperature within the plasma frame, which is a way of describing particle motion rather than physical warmth. Alongside this energy increase, Voyager also detects a spike in particle density, which means that the number of charged particles in a given region of space rises suddenly compared to nearby regions. And this happens because the solar wind, which has been flowing outward from the Sun for billions of miles, begins to interact more strongly with the interstellar medium, which is the thin gas and plasma that fills the space between stars. And when these two flows meet, they do not merge smoothly. Instead, they compress, bend, and push against each other, creating regions where particles pile up more than expected in certain areas. And this uneven distribution of particles creates sharp variations in the data, even though the underlying structure is still spread out across large distances. The temperature readings that reach tens of thousands of Kelvin, and sometimes higher, are one of the most misunderstood parts of this entire region. Because when people hear numbers like 50,000 degrees Celsius or 100,000 K, the natural assumption is that something extremely hot is present, in a way that would destroy a spacecraft or create intense heat. But in reality, these values come from measuring particle motion in a very low-density environment where collisions are rare, and temperature in this context is defined by how fast particles are moving on average, rather than how much heat is transferred between them. So a small number of fast-moving particles can create very high temperature readings, even though the actual energy available to heat a solid object is extremely low due to the lack of matter. This is where the difference between space plasma and everyday experience becomes important, because on Earth temperature is linked to how energy spreads through large numbers of particles that constantly collide. But in deep space, the number of particles is so low that even when individual particles move very fast, they do not interact often enough to create continuous heat transfer, which means that a spacecraft passing through this region does not experience any physical heating effect even when instruments report extremely high temperature values, because those values reflect microscopic motion rather than macroscopic thermal energy. The reason this region is sometimes described in public discussions as a wall comes from the way these sudden changes appear in simplified graphs and summaries of the data, because when particle density, energy levels, and magnetic field strength are plotted over time, the transitions between different regions can look sharp, especially when Voyager moves from one plasma environment to another over a relatively short period of time compared to the long journey through space. And these sharp changes create visual patterns that resemble a boundary or a barrier, even though the actual structure is more like a gradual but uneven transition zone shaped by interacting flows of charged particles. Another reason this wall description spreads is because the heliosphere itself is not a smooth and uniform structure, since the solar wind does not expand into space evenly in all directions, and the interstellar medium does not push back with equal strength everywhere. So the boundary region where these two pressures meet becomes uneven and unstable, with some areas showing stronger compression and others showing weaker interaction. And this unevenness can create localized regions where changes happen more quickly, which again can be misread as a sharp edge when viewed without the full context of how large and spread out these interactions actually are. Voyager's instruments detect these changes not as a single event, but as a combination of different signals that shift over time. Because the plasma wave instrument measures electron density, the cosmic ray detector measures high-energy particles coming from outside the solar system, and the magnetometer tracks changes in magnetic field direction and strength. And each of these instruments responds to different aspects of the environment. So when all of them show changes around the same general region, it creates a strong impression of a distinct boundary, even though each measurement is responding to a different physical process that is unfolding gradually across space. The plasma energy jump is especially linked to the way the solar wind slows down as it approaches the outer regions of its influence, because as the outward flow loses speed due to interaction with the interstellar medium, the energy carried by that flow does not disappear, but instead gets redistributed into random particle motion, which increases the measured energy per particle, and this redistribution is not uniform. So some regions show stronger increases than others, depending on how local magnetic fields and particle streams interact at that moment. And this uneven energy distribution adds to the impression of sudden change. The particle density spike is also tied to compression effects that happen when two large-scale flows meet, because the solar wind is still moving outward while the interstellar medium is pushing inward. And where these flows meet, particles can become compressed into narrower regions before spreading out again. And this compression is not constant or stable, but changes over time as the strength of the solar wind varies with solar activity, meaning that Voyager can pass through regions where density appears higher for a short time, before entering areas where it drops again, creating a pattern of fluctuations rather than a single consistent layer. Magnetic field changes add another complexity to this region, because magnetic fields in space are carried by moving charged particles. And when those particles slow down, change direction, or mix with other particle streams, the magnetic field lines become distorted, stretched, or reoriented, and this creates turbulence in the magnetic structure of the region, where field strength and direction can vary depending on local conditions. And these variations can happen over relatively short distances compared to the overall scale of the heliosphere, making the boundary region appear more active and structured than simple models would suggest. What temperature means in deep space. Temperature in deep space does not behave in the same way as temperature on Earth, because what is being measured is not heat that spreads through air or water or solid material, but the average energy of individual particles moving through an almost empty environment where collisions are extremely rare. And this difference changes everything about how readings from Voyager should be understood. Because when instruments report extremely high temperatures in regions far from the Sun, it does not mean that the spacecraft is passing through something physically hot in the way fire or hot metal is hot. Instead, it means that the few particles present in that region are moving very fast or carrying a large amount of kinetic energy, even though they are spread out so thinly that they cannot transfer that energy in a way that produces heat in the usual sense. In space near Earth, or even near the outer planets, temperature is already not a simple concept, but as distance increases and particle density drops further, the meaning of temperature becomes even more tied to motion rather than sensation or physical warmth. Because in a normal environment like air on Earth, temperature works through constant collisions between huge numbers of particles, where energy is constantly passed from one particle to another, creating a stable and uniform feeling of heat or cold, depending on how fast those particles are moving on average. But in deep space, the number of particles is so extremely low that these collisions almost never happen, and without frequent collisions, there is no efficient way for energy to spread evenly across a region, which means that temperature becomes a statistical measurement of particle speed rather than a physical condition that can be felt or transferred. Voyager passes through regions where a small number of particles can reach very high speeds, especially in areas where solar wind particles are still present or where interstellar particles are being accelerated by magnetic fields and shock regions. And when instruments measure these particles, they record their kinetic energy and convert that into a temperature value, which can easily reach tens of thousands, or even over 100,000 Kelvin. But this number does not represent a hot environment in the way people normally imagine, because the key missing factor is density. Since there are so few particles in these regions that even if each particle carries high energy, there is not enough material to transfer that energy into heat that could affect an object like a spacecraft. This is where the concept of hot but empty space becomes important, because Voyager is moving through regions where particle energy is high, but particle count is extremely low, meaning that the energy is spread across a very small number of particles in a very large volume of space. And this creates a situation where temperature readings look extreme on paper, but do not correspond to any physical heating effect on the spacecraft, since heating requires continuous collisions and energy transfer between many particles, and without that density, there is no mechanism for heat to build up in a way that would be felt or measured as thermal energy on an object's surface. One way to understand this is to think about how temperature would normally be measured in air, where every molecule is constantly bumping into other molecules, transferring energy in all directions, and creating a stable environment where a thermometer can pick up those changes easily. But in deep space, the thermometer is replaced by particle detectors that are not measuring heat in the traditional sense, but instead measuring individual particle velocities. And when those velocities are high, the calculated temperature becomes high, even though the actual environment remains extremely thin and unable to transfer that energy in any meaningful way to large objects, which is why spacecraft like Voyager can survive in regions where temperatures appear extreme in data, but where there is almost no matter to create physical heat. The reason a single particle can be described as extremely hot in energy terms is because temperature at the particle level is directly linked to how fast that particle is moving. So if a proton or electron is traveling at very high speed, it carries a large amount of kinetic energy, and when many such particles are measured together, their average energy defines the temperature of that region. But this average does not reflect how much energy can be transferred to a solid object, because the key factor missing is interaction. And in deep space, interaction between particles is so rare that energy remains mostly isolated within individual particles rather than spreading across a system. As Voyager moves through different regions of space, it encounters changes in particle energy that reflect transitions between solar wind-dominated regions and interstellar regions. And in each of these regions, the particles behave differently depending on whether they are still influenced by the sun's outward flow or by the surrounding galactic environment. And when solar wind particles slow down or collide with interstellar particles, they can gain or lose energy in ways that create spikes in measured temperature, even though the environment itself remains extremely thin and unable to support conventional heat transfer. The solar wind itself plays a major role in shaping these temperature readings because it is a continuous stream of charged particles moving outward from the sun at high speed. And when this stream travels far from the sun, it begins to interact with particles already present in interstellar space. And this interaction does not happen in a smooth or uniform way. Instead, it happens in patches and regions where particles collide or are compressed by magnetic fields. And in these regions, particle speeds can increase suddenly, which leads to local increases in measured temperature, even though the overall density remains extremely low. This is why Voyager can record regions that appear extremely hot in data while still moving through space that would feel colder than almost anything experienced near Earth. Because feeling temperature requires a medium that can transfer energy through collisions. And in deep space, that medium is almost missing entirely, leaving only isolated particles that carry energy but do not share it efficiently, meaning that temperature becomes more of a description of motion than of physical condition. The distinction between energy per particle and total energy in a region of space is critical for understanding these readings, because a region can have very high energy particles while still containing almost no total energy overall, since the number of particles is so small that the total amount of heat that could be transferred is negligible. And this is why spacecraft are not affected by these high temperature readings. Because what matters for heating is not how fast individual particles move, but how many of them are present, and how often they collide with a surface to transfer that energy. Voyager's instruments are designed to measure these particle energies directly, which means they are sensitive to individual particle motion rather than bulk heat. And when they pass through regions where particle acceleration occurs, such as near shock boundaries or magnetic disturbances, they detect sudden increases in energy levels that translate into high temperature readings. But these readings must always be interpreted in the context of extremely low density. Otherwise, they can be easily misunderstood as physical heat rather than statistical motion. The environment that Voyager moves through after leaving the main solar wind region still contains enough structure to influence particle behavior, because magnetic fields extend far beyond the planets and continue shaping how charged particles move. And when these fields interact with interstellar plasma, They can create regions where particles are accelerated or compressed, leading to variations in energy levels that appear as temperature changes in the data, even though the underlying process is driven by electromagnetic forces rather than thermal heating in the traditional sense. Even in regions where the solar influence becomes weaker, the residual effects of the solar wind continue to shape particle motion, because the outward flow does not stop abruptly but gradually loses strength, and as it weakens, it creates areas where particles slow down unevenly and interact with incoming interstellar particles, producing localized regions of higher energy that Voyager can detect as spikes in temperature and density, reinforcing the picture of space as a highly structured environment, even at extreme distances from the Sun. The key point in all of this is that temperature in deep space is not a measure of how hot something feels or how much heat is present in a region, but a measure of how energetic individual particles are on average. And when those particles are extremely fast but extremely few, the result is a reading that looks extreme but represents a very different physical reality than what temperature means on Earth. Which is why Voyager can pass through what is described as hot but empty regions, where energy is high at the microscopic level but almost absent at the macroscopic level, creating a situation where space can appear both energetic and empty at the same time without contradiction in the actual physics involved. The heliopause, true edge of solar influence. The heliopause is not a surface, line, or a place where space suddenly changes like a switch being turned on or off, but a wide pressure boundary where two massive flows of particles meet and balance each other. One flow coming outward from the Sun in the form of the solar wind, and the other coming inward from the galaxy as interstellar particles and magnetic fields that fill the space between stars. And this balance point is what defines the outer limit of the Sun's main influence. Not because something physical stops there, but because the outward force from the Sun becomes equal to the inward pressure from the surrounding interstellar medium. And at that exact balance, the solar wind can no longer push outward with dominance, so its structure begins to break down, spread out, and mix with outside material in a way that creates a large and uneven transition region rather than a clean boundary. The solar wind is not a static thing. It is a continuous flow of charged particles coming from the outer atmosphere of the Sun, and it moves outward in all directions carrying energy, magnetic fields, and plasma that fills the entire space around the planets. And for billions of miles, this flow maintains a strong outward pressure that shapes the heliosphere, which is the large bubble-like region around the solar system. But as this flow moves farther away from the Sun, it spreads out and weakens, because the same amount of material is being distributed across a much larger volume of space, and at the same time it begins to encounter the interstellar medium, which is not empty either, but contains its own particles and magnetic fields. And when these two environments meet, they do not merge smoothly. Instead, they push against each other in a slow but constant interaction that creates a region of compression, turbulence, and shifting boundaries. The heliopause forms at the point where the outward pressure of the solar wind is no longer stronger than the inward pressure of the interstellar medium, meaning that neither side fully wins in that region, and instead a balance is reached where both forces push against each other with equal strength. And this balance does not produce a stable surface, but a dynamic zone that shifts depending on changes in solar activity and variations in the density of interstellar space. So the heliopause is not fixed in one location, but can move inward or outward over time, depending on how strong the solar wind is at any given moment. Which means that Voyager did not cross a single permanent line, but passed through a changing region that behaves differently depending on local conditions in space. When Voyager 1 crossed this region in 2012, the instruments did not record a single sudden event that marked a clear entrance into interstellar space. Instead, they recorded a sequence of changes that unfolded over time, starting with a sudden drop in the number of solar particles detected, which showed that the influence of the solar wind was weakening significantly, followed by a rise in galactic cosmic rays, which are high-energy particles coming from outside the solar system, often from distant supernovae and other energetic events in the galaxy, and this rise indicated that the protective bubble of the solar wind was no longer blocking these particles as strongly as before, allowing more of them to reach the spacecraft. At the same time, Voyager recorded changes in the magnetic field, where the direction and strength of the field began to shift in ways that were not fully aligned with earlier measurements inside the heliosphere. And this shift did not happen as a sudden flip, but as a gradual adjustment, showing that the magnetic environment in this region is not controlled by a single dominant source, but is influenced by both the outgoing solar magnetic field and the surrounding interstellar magnetic field, which begin to interact and overlap in this boundary zone, creating a mixed field structure that does not behave like either region alone. Voyager 2 crossed the same general boundary in 2018, but in a different location and under slightly different conditions, and it also recorded similar patterns, including a drop in solar particle counts, a rise in cosmic ray intensity, and changes in magnetic field behavior. But the timing and strength of these changes were not identical to Voyager 1, because the heliopause is not uniform across all directions. Instead, it has different shapes and distances depending on how the solar wind interacts with the surrounding interstellar medium in different parts of space, which means each crossing provides a slightly different picture of how this boundary behaves. The sudden drop in solar particles is one of the clearest indicators that a spacecraft is moving away from the main influence of the Sun, because inside the heliosphere, the solar wind is a constant and dominant flow, filling space with charged particles moving outward. But as Voyager approaches the heliopause, this flow weakens to the point where it can no longer maintain a strong presence, and instead begins to blend with incoming interstellar particles. So the instrument readings show a sharp decline in solar origin particles, not because they disappear instantly, but because their density becomes much lower compared to the surrounding environment, making them less dominant in the data. At the same time, the rise in galactic cosmic rays becomes more noticeable, because outside the heliosphere, there is no longer a strong solar wind barrier blocking high-energy particles from entering the inner regions. So more of these particles, which originate from distant and powerful cosmic sources, begin to move freely into the region where Voyager is located. And this increase is not just a small change, but a significant shift in particle environment, showing that the spacecraft is now in a region where external galactic processes have more influence than the Sun itself, even though the Sun is still present in the background as a distant source of gravity and residual magnetic influence. The magnetic field shift in this region is one of the most complex parts of the heliopause, because magnetic fields in space are carried by moving charged particles, and inside the heliosphere, these fields are mainly shaped by the solar wind, which carries the Sun's magnetic influence outward. But as the solar wind slows down and weakens near the heliopause, it begins to interact more strongly with the interstellar magnetic field, which comes from outside the solar system and has its own structure and direction. And when these two fields meet, they do not cancel or merge cleanly. Instead, they overlap and create regions of distortion where the direction of the field changes gradually or fluctuates, depending on local conditions. This overlapping magnetic structure means that Voyager does not pass through a clean magnetic boundary, but instead moves through a region where field lines from both the Sun and the galaxy are present at the same time, creating a mixed environment where magnetic forces are constantly adjusting to the balance between outgoing and incoming pressure. And this makes the heliopause not just a boundary of particles, but also a boundary of magnetic influence, where two large-scale systems meet and interact in a way that is spread out over a wide distance, rather than concentrated in a single point. The pressure balance that defines the heliopause is also not static, because both the solar wind and the interstellar medium can change over time, meaning that the location of the heliopause can shift depending on changes in solar activity, such as solar storms or variations in the Sun's output, and also depending on variations in the density and pressure of interstellar space, which is not uniform but contains regions of different density and magnetic strength. So the boundary moves slightly in response to these changing conditions, making it a dynamic structure rather than a fixed edge. Voyager's measurements across this region show that even after crossing into interstellar space, the environment does not become suddenly uniform or empty. Instead, it continues to show variations in particle density, energy levels, and magnetic field direction, indicating that the heliopause is not a final barrier, but part of a larger transition into the interstellar medium, where the influence of the Sun gradually fades rather than stopping abruptly, and where the galaxy's background environment becomes more dominant over time, but still contains its own structure and variations that continue to affect any object moving through it. The shock-like wall effect. Voyager does not meet a wall in space, not a solid surface, a barrier made of matter, not even anything that could physically stop a spacecraft or reflect it back. But what it does pass through is a region where multiple measurements change in ways that happen quickly over relatively short distances compared to the long journey through the outer solar system. And when these changes are plotted from instrument data, they can look like sharp edges, sudden breaks, or steep transitions, and this visual pattern is what creates the shock-like wall effect, even though the physical reality is a broad and uneven interaction zone where particle flows, magnetic fields, and energy levels adjust to each other in steps, rather than in a single, clean boundary. The first reason this effect appears is because particle density in this region does not fall smoothly or evenly. Instead, it shifts in patches where solar wind particles and interstellar particles interact, and these patches can form areas where density rises quickly over a short distance, followed by regions where it drops again. And this uneven structure is not random, but comes from the way two large-scale plasma flows collide, because the solar wind is still moving outward while interstellar particles are pushing inward. And where these two flows meet at different angles and speeds, compression happens in certain zones, while expansion happens in others, creating a layered pattern of density changes that can appear sharp when viewed through the limited sampling of a spacecraft moving at high speed through the region. This sharp change in density is one of the strongest reasons the region can look like a wall in the data, because when Voyager's instruments measure particle counts over time, they do not capture every microscopic variation in space. Instead, they take continuous but discrete measurements as the spacecraft moves forward, and when it passes through a region where density changes rapidly over a short distance, those measurements appear as a sudden jump from one level to another, even though between those points there is still a gradual transition that is simply not fully resolved by the sampling resolution of the instruments. The second major factor is the way magnetic fields behave in this boundary region, because magnetic fields in space are not static lines, but structures carried by moving charged particles. And when those particles slow down, compress, or mix with incoming interstellar plasma, the magnetic field lines become distorted, twisted, and reoriented in response to changing flows. And this creates regions where the direction of the field can shift noticeably over relatively short distances, which appears in the data as sudden changes in magnetic field orientation, even though in reality the field is adjusting continuously to local conditions shaped by both solar and interstellar influences. These magnetic shifts are especially important in creating the shock-like appearance, because magnetic fields influence how charged particles move, and when the field direction changes, particle motion also changes, leading to changes in energy distribution and density at the same time. So multiple instrument readings can shift together within a similar region, reinforcing the impression that something sharp or defined is being crossed, when in reality it is the result of overlapping magnetic structures interacting in a complex way that unfolds across space and time rather than at a single point. The third factor comes from the abrupt drop in solar wind speed as Voyager moves farther from the Sun and approaches regions where the outward pressure of the solar wind is no longer strong enough to maintain its high-speed flow, because as the solar wind travels outward, it gradually loses energy and spreads over a larger volume of space. And when it reaches regions where interstellar pressure becomes more significant, the flow slows down in a way that is not uniform, because different streams of solar wind particles can slow at different rates depending on local density and magnetic conditions, creating uneven velocity transitions that appear as sharp drops in instrument readings when averaged over time. This slowing of the solar wind does not mean the particles simply stop moving forward. Instead, it means their organized outward motion is converted into more random motion, where particles scatter in different directions rather than flowing as a coherent stream. And this conversion of motion changes how instruments interpret speed and energy, producing data that shows rapid changes over relatively short distances, again contributing to the impression of a boundary that behaves like a wall, even though it is actually a region where flow structure is breaking down gradually under increasing external pressure. Instrument limitations also play a major role in strengthening the shock-like wall effect, because Voyager's instruments are extremely advanced for their time, but still limited in resolution compared to the scale and complexity of the environment they are measuring. And as the spacecraft moves through vast regions of space, it samples conditions along a narrow path at a fixed speed, which means it cannot capture every small variation in particle density or magnetic field strength that exists in the surrounding volume. So when conditions change quickly relative to the sampling rate, the recorded data shows step-like transitions instead of smooth gradients, which reinforces the appearance of sharp boundaries in graphs and charts. This limitation becomes more noticeable in regions where multiple variables change at the same time, because in the outer heliosphere, particle density, magnetic field strength, and solar wind speed are all changing together as Voyager moves outward. And when several variables shift in overlapping regions, the combined effect in the data can look like a coordinated jump, even though each individual process is still happening continuously and independently at different scales. And this overlap of changes is what makes the region visually appear more structured than it actually is when seen through instrument readings alone. Another important part of the shock-like wall effect is the way energy is redistributed in this region. Because when the solar wind slows down due to interaction with the interstellar medium, its kinetic energy does not disappear but is transferred into particle motion and local heating in the plasma frame, which increases the average energy per particle in certain regions. And this change in energy distribution often happens alongside density and magnetic changes, creating correlated shifts across different types of measurements, which makes the transition appear even sharper when all data streams are viewed together. The interaction between solar wind and interstellar medium is not smooth because both environments have different properties, with the solar wind being a fast-moving, outward-flowing plasma dominated by the sun's influence, and the interstellar medium being a slower, more diffuse mixture of particles and magnetic fields that fills the space between stars. And when these two environments meet, they do not blend evenly, but instead form regions of compression, turbulence, and mixing layers where properties change rapidly over distance. And these mixing layers are what Voyager passes through as it approaches and crosses the outer boundary of the heliosphere. Inside these mixing regions, particles can be accelerated or decelerated depending on local conditions, and this creates localized variations in energy and density that contribute to sudden changes in instrument readings, because one region may contain relatively slow-moving particles, while a nearby region contains particles that have gained energy from magnetic interactions or shock compression. And when Voyager moves between these regions, the transition appears sharp, because the difference in conditions between adjacent areas can be significant, even though the underlying structure remains continuous. The shock-like appearance is also strengthened by the fact that space at this distance is extremely large and sparsely populated, which means that even small changes in particle density or energy can represent large relative differences. So when measurements are plotted over time, these relative changes can appear more dramatic than they would in a denser environment, where similar variations would be smoothed out by frequent collisions and energy exchange between particles. What Voyager actually detected at the edge. Voyager did not pass through a single clear event that can be described as one simple change in space. Instead, it recorded a combination of different shifts happening across different instruments at roughly the same region of space. And each instrument was measuring a different part of the environment, which means the full picture only appears when all of them are looked at together. And what they show is not a wall or a boundary in the physical sense, but a region where particle flows, radiation levels, and magnetic structures all change their behavior over distance in ways that can appear sudden when viewed from a moving spacecraft sampling a vast and complex region of plasma. The plasma wave subsystem is one of the most important tools Voyager carried for understanding the outer regions of the solar system, and it works by detecting waves in the plasma that surrounds the spacecraft, which are created when charged particles move through space and interact with each other and with magnetic fields. And what this instrument recorded near the outer boundary was a clear jump in electron density, meaning that the number of free electrons in the surrounding space increased noticeably compared to regions closer to the Sun. And this change did not happen gradually over a small visible region, but instead appeared as a distinct shift in the data as the spacecraft moved forward, showing that the environment was changing in structure over distance. This electron density jump is important because electrons are part of the plasma that fills space, and their density reflects how much interaction is happening between different particle populations. So when Voyager recorded a sudden increase in electron density, it indicated that the spacecraft was moving into a region where the solar wind was interacting more strongly with interstellar material, causing particles to become compressed or redistributed in ways that increase local density. And this increase was not uniform across all directions, but depended on how the solar wind and interstellar medium were meeting at that particular region of space, which created uneven patches of density that the spacecraft passed through in sequence. The cosmic ray detector provided another key piece of information, because it measured high-energy particles coming from outside the solar system, and what it showed was a clear increase in galactic cosmic radiation as Voyager moved closer to and eventually past the outer boundary of the heliosphere. And this increase happened because the solar wind, which normally acts as a kind of protective flow that reduces the number of high-energy particles entering from outside, was weakening in that region, allowing more cosmic rays from distant sources in the galaxy to reach the spacecraft. And this change in radiation levels did not happen as a smooth slope, but appeared as a noticeable rise over a relatively short range of measurements, showing that the protective influence of the solar wind was no longer dominant in that region. This rise in galactic radiation is important because it shows a shift in control over the local environment, where inside the heliosphere, the Sun's outward flow dominates particle movement and shields the inner region from many external high-energy particles. But near and beyond the boundary region, this shielding becomes less effective, and cosmic rays begin to appear in greater numbers, not because they suddenly appear at a single point, but because the conditions that block them are gradually breaking down as the solar wind weakens and interacts more with interstellar space, allowing more of these external particles to pass through the region where Voyager is traveling. The magnetometer on board Voyager measured changes in the magnetic field, which is carried through space by charged particles and shaped by their motion. And what it detected near the boundary region was a reorientation of the magnetic field lines, meaning that the direction and structure of the field began to shift compared to what was measured inside the main solar wind region. And this shift was not a sudden flip or break, but a gradual adjustment influenced by both the solar magnetic field carried outward by the solar wind and the interstellar magnetic field that exists outside the solar system. And as these two fields met in the boundary region, they began to overlap and interact, creating a mixed magnetic environment where field lines were not fully aligned with either system, but instead showed signs of combined influence. This reorientation is significant because magnetic fields control how charged particles move in space, and when the direction of the field changes, particle motion also changes, which affects density, energy, and radiation levels in the surrounding region. So the changes detected by the magnetometer are directly linked to the changes seen by the plasma wave subsystem and the cosmic ray detector, creating a connected picture of a region where multiple physical processes are changing at the same time, each influencing the others through magnetic and particle interactions that extend over large distances. The engineering subsystem, which monitors the spacecraft's own internal conditions, also recorded subtle changes during this transition, particularly in temperature stability, which reflects how the spacecraft responds to the external environment even though it is designed to operate in extreme conditions. And while Voyager itself is not affected by heat in the same way a human or an atmosphere would be, its systems can still register changes in external particle environment through small variations in temperature readings of its instruments and components. And during the crossing of the outer boundary region, these readings showed minor fluctuations that corresponded with changes in particle density and radiation levels outside the spacecraft. These engineering measurements are important because they provide a reference point that helps confirm that the changes seen in scientific instruments are real environmental shifts rather than instrument errors. Since multiple systems reacting at the same time to the same region of space suggests that the spacecraft is passing through a physically different environment and not just experiencing random fluctuations in a single instrument. And when these engineering signals are combined with plasma, radiation, and magnetic data, they form a consistent pattern that indicates a transition into a different plasma regime. The electron density jump recorded by the plasma wave subsystem, the rise in galactic cosmic rays recorded by the radiation detector, the magnetic field reorientation measured by the magnetometer, and the small stability changes recorded by engineering systems all occur within the same broad region of space, but not in exactly the same moment or location, because each process responds differently to local conditions and interacts with space at different scales, which means the spacecraft moves through a layered transition zone where different physical effects become noticeable at different points along its path. This layered structure is important because it shows that the outer boundary of the solar system is not a single event or surface, but a region where different physical systems overlap and change at different rates. And Voyager's instruments capture these changes as a sequence of shifts rather than a single step, with each instrument highlighting a different part of the same environmental transition, whether it is particle density increasing, radiation levels rising, magnetic fields changing direction, or internal spacecraft readings adjusting slightly in response to the surrounding plasma conditions. The interstellar medium, what lies beyond? The space beyond the heliopause does not turn into emptiness, blank void where nothing exists, and it does not suddenly lose structure just because the sun's main influence has weakened. Instead, it becomes a different kind of environment that is still filled with matter and energy, but in a much thinner and more spread out form. And this region is called the interstellar medium, which stretches across the space between stars in the galaxy and forms the basic background environment that everything else in the Milky Way moves through, including solar systems, star clusters, and large clouds of gas that eventually form new stars over long periods of time. The interstellar medium is not uniform. It is not the same everywhere, and it does not behave like a still background field because it is made up of different components that exist together, but do not always mix evenly, including hydrogen plasma, cosmic dust, and large-scale galactic magnetic fields, and each of these components has its own structure, motion, and energy level, which means that even though the density is extremely low compared to anything near planets or stars, the region is still active and shaped by continuous physical processes that extend across huge distances in space. Hydrogen plasma forms one of the main components of this medium, and it exists as extremely thin gas made mostly of protons and electrons that have been separated due to energy from stars and cosmic radiation. And even though this plasma is very sparse, it still carries electrical charge and responds to magnetic fields, which means it is not static, but constantly moving and adjusting based on large-scale forces in the galaxy and in different regions of interstellar space This plasma can vary in density, temperature and motion depending on nearby stars, shock waves from supernova remnants, or interactions with large molecular clouds, which makes the environment far from uniform even though it appears empty from a human perspective. Cosmic dust is another part of the interstellar medium, and it consists of very small solid particles made from elements like carbon, silicon, oxygen and iron. And these particles are extremely small compared to anything visible to the human eye, but they are spread across vast distances in space, and while their density is very low, they still play an important role in shaping the structure of interstellar space, because they can absorb and scatter light, affect the temperature of surrounding gas, and act as seeds for the formation of larger structures over long periods of time, especially in regions where gravity begins to pull material together into denser clouds. The galactic magnetic field is another key component of this region, and it is a large-scale magnetic structure that stretches across the Milky Way galaxy, shaping the movement of charged particles and influencing how plasma flows through interstellar space. And unlike the magnetic field near a planet or a star, which is more localized and stronger in intensity, the galactic magnetic field is extremely weak in strength, but spread across enormous distances, and even though it is weak, it still has a significant effect on the motion of charged particles, like those found in hydrogen plasma, guiding their movement along large-scale patterns that can extend for light years. When Voyager moves beyond the heliopause and enters this region, it does not suddenly find empty space. Instead, it begins interacting with a different kind of plasma environment, where the influence of the Sun is no longer the dominant force shaping particle behavior, and instead the structure of space is controlled more by the galactic environment, where particles are influenced by magnetic fields that come from outside the solar system, and where the density of matter is low, but still enough to create measurable effects on spacecraft instruments over time. The hydrogen plasma in this region behaves differently from the solar wind plasma inside the heliosphere, because inside the heliosphere, the plasma is dominated by a strong outward flow driven by the Sun, which gives it a clear direction and structure. But in the interstellar medium, there is no single dominant source pushing particles outward, so the plasma moves more slowly and is influenced more by local magnetic fields and distant astrophysical events, which creates a more varied and less directional flow of particles, where motion is guided by a combination of weak forces rather than a single strong source. Cosmic dust in this region does not form dense clouds everywhere, but instead exists as scattered particles that drift through space, sometimes gathering in slightly denser regions where gravity or magnetic fields begin to pull material together. And while Voyager does not directly interact strongly with dust particles due to the extreme distances between them, the presence of dust still matters because it reflects the overall structure of the interstellar environment, showing that space is not truly empty but contains a mix of solid particles and gas spread across enormous volumes. The temperature behavior of the interstellar medium is also very different from what is experienced in planetary environments, because temperature here refers again to particle energy rather than heat in the usual sense. And in many regions the density is so low that even if particles carry high energy, they do not transfer that energy through collisions in a way that produces warmth, which leads to a situation where space can contain extremely energetic particles while still remaining effectively cold in terms of heat transfer. And this combination of low density and high energy creates a unique environment where traditional ideas of temperature do not directly apply. Voyager entering this region begins to record changes in particle composition and energy distribution, because the balance between solar particles and interstellar particles shifts, and instead of being surrounded mainly by solar wind particles moving outward, the spacecraft begins to detect a higher proportion of particles that come from outside the solar system. And these particles often have different energy levels and motion patterns compared to those inside the heliosphere, which leads to changes in instrument readings that reflect this transition into a new plasma regime. This new plasma regime is not uniform across all directions because the interstellar medium itself has variations in density and magnetic structure, meaning that Voyager does not enter a single consistent environment, but instead passes through regions where conditions change gradually over distance, with some areas showing slightly higher particle density or different magnetic orientations compared to nearby regions. And these variations create a layered structure in the data that reflects the complexity of the galactic environment rather than a simple boundary between two regions. The interaction between Voyager and this interstellar plasma is shaped by the fact that the spacecraft is still moving through a region influenced by both residual solar effects and the surrounding galactic environment, which means that even after crossing the heliopause, there is still some overlap between the two systems, where weak solar influence and stronger interstellar conditions exist together in a transitional zone that continues to evolve as the spacecraft moves further away from the Sun. Hydrogen plasma in this region can vary in energy depending on local conditions, because it can be influenced by distant astrophysical events such as supernova remnants that send shock waves through space, or by magnetic field interactions that accelerate particles over large distances. And these variations in energy mean that Voyager can detect changes in particle speed and density even in regions that are far from any star system, showing that interstellar space is still an active environment shaped by large-scale cosmic processes. The galactic magnetic field plays a key role in organizing this environment, because even though it is weak compared to magnetic fields near stars or planets, it extends across the galaxy and influences how charged particles move over long distances. And as Voyager travels through this field, it experiences changes in magnetic orientation and strength that reflect the structure of the galaxy itself, rather than the structure of the solar system, marking a shift from a locally dominated environment to one shaped by much larger cosmic scales. Why the region is extremely hot in data terms. The region near and beyond the outer edge of the solar system shows temperature readings that look extreme on paper, sometimes reaching tens of thousands or even over 100,000 Kelvin. And at first glance, these numbers can give the impression that Voyager is moving through something physically hot in the normal sense. But what is actually happening is tied directly to how energy behaves in a plasma that is extremely thin, where particles are so widely spread out that collisions are rare, and where energy is carried mostly by individual particle motion rather than shared heat, which creates a situation where temperature readings reflect motion at the microscopic level rather than thermal conditions that would be felt or transferred to an object. Rare particle collisions are one of the main reasons behind these high temperature values, because in most environments on Earth, or even inside planetary atmospheres, temperature comes from constant collisions between huge numbers of particles, where energy is passed from one particle to another in a continuous chain that creates a stable and uniform thermal state. But in the outer regions of space where Voyager is traveling, the number of particles in a given volume is extremely low, which means that collisions between them happen very infrequently. And when collisions are rare, energy does not spread evenly. Instead, it remains concentrated in individual particles that can move at very high speeds. And when instruments measure these particles, they detect their kinetic energy directly, which translates into very high temperature values, even though the environment as a whole does not behave like a hot gas in the normal sense. These rare collisions also create uneven energy distribution, because some particles may carry much more energy than others, depending on how they were accelerated or influenced by magnetic fields or shock regions. And since there are so few particles overall, the presence of even a small number of highly energetic particles can raise the average energy reading significantly, which again increases the temperature value reported by instruments, even though the actual number of particles available to transfer heat remains extremely low, meaning that the high temperature reading is not linked to a physically hot environment, but instead to a statistical measurement of particle motion in a very low density region. Shock compression effects also play a major role in creating these high energy readings, because as the solar wind moves outward from the Sun and eventually slows down near the outer boundary of the heliosphere, it does not simply fade away smoothly. Instead, it encounters resistance from the interstellar medium. And when a fast-moving flow of charged particles is slowed down abruptly by an external pressure, the energy in that flow does not disappear. It is redistributed into different forms, including increased random motion of particles and localized heating in the plasma frame, which leads to regions where particle energy increases significantly over relatively short distances compared to the overall scale of space. This compression does not happen in a single uniform layer, but in uneven regions where different parts of the solar wind slow down at different rates depending on local conditions. And when these compressed regions form, they create zones where particles are packed more closely together than in surrounding space, which increases the likelihood of collisions and raises the average energy per particle, leading to spikes in temperature readings that Voyager detects as it passes through these regions. And these spikes are not constant, but vary depending on how the spacecraft moves through different parts of the compressed flow. Magnetic reconnection events add another layer of energy transfer in this region, because magnetic fields in plasma are not fixed structures, but flexible and dynamic fields carried by moving charged particles. And when magnetic field lines with different directions come into contact, they can break and reconnect in new configurations, releasing stored magnetic energy into particle motion, which accelerates particles and increases their kinetic energy. And when this happens in regions with low particle density, even a small amount of released energy can significantly increase the average energy per particle, contributing to higher temperature readings in the data collected by Voyager. These reconnection events do not happen at a single point, but occur across extended regions where magnetic fields from the solar wind interact with those from the interstellar medium. And as these fields overlap and adjust to each other, energy is constantly being transferred between magnetic structure and particle motion, creating a dynamic environment where energy levels fluctuate depending on local interactions. And Voyager, passing through these regions, records these fluctuations as changes in particle energy that contribute to the overall high temperature readings seen in the outer heliosphere. Energy transfer from the solar bubble boundary is another important factor, because the heliosphere itself acts as a large region filled with solar wind plasma that carries energy outward from the Sun. And as this flow reaches its outer boundary, energy is not simply lost. Instead, it is redistributed into the surrounding environment where it interacts with interstellar particles. And this transfer process creates regions where energy becomes concentrated in certain particles or areas of space, leading to localized increases in particle motion that are recorded as higher temperatures by spacecraft instruments. This energy transfer is not uniform because the boundary of the heliosphere is not smooth. It is shaped by variations in solar activity and differences in the density of interstellar space, which means that some regions of the boundary are more compressed than others. And in these compressed regions, energy transfer is more intense, leading to stronger increases in particle motion and higher temperature readings, while in other regions the interaction is weaker and energy levels are lower, creating a patchy structure of energy distribution across the boundary region. As all these processes combine, rare particle collisions, shock compression effects, magnetic reconnection events, and energy transfer from the solar bubble boundary, they create a region where individual particles can carry extremely high energy, even though the overall environment remains extremely thin. And this combination is what leads to the very high temperature values reported in the data, which reflect particle motion rather than thermal conditions in the traditional sense. Alongside these energy-related effects, Voyager also recorded a surprising and important magnetic field behavior in the same region, where instead of seeing a sharp break or sudden reversal in the magnetic field at the boundary of the heliosphere, the spacecraft detected a smoother transition, where the magnetic field outside the heliosphere appeared to be aligned with the field inside, which was unexpected because earlier models had suggested that the boundary between solar and interstellar space would show a more distinct change in magnetic direction. This strange alignment led to what is sometimes referred to as the magnetic highway region, where magnetic field lines from inside and outside the heliosphere appear to connect or align in a way that allows particles to move more smoothly between regions, rather than being blocked or sharply redirected at a boundary. And this behavior suggests that the transition between solar and interstellar space is more gradual in magnetic terms than previously thought, with field lines adjusting and blending over a wide region rather than forming a sharp discontinuity. This alignment does not mean that the solar magnetic field and the interstellar magnetic field are identical, but rather that in certain regions near the boundary, the two fields can orient in similar directions due to the way they interact under pressure balance conditions. And when this happens, charged particles can move along these aligned field lines more easily, creating pathways where particle movement is less restricted, which contributes to smoother transitions in magnetic readings instead of abrupt changes. Voyager's magnetometer data shows that instead of encountering a sudden flip in field direction at the heliopause, the spacecraft passed through a region where magnetic field direction gradually adjusted over distance, influenced by both solar wind dynamics and interstellar magnetic structure. And this gradual adjustment indicates that the boundary is not a simple dividing line, but a wide interaction zone, where different magnetic systems overlap and influence each other continuously. Cosmic ray surge. The big surprise. Cosmic rays are one of the clearest signs that Voyager has moved into a different kind of space environment, because inside the heliosphere, the Sun is not just a source of light and heat. It is also a powerful shield that pushes outward through the solar wind and carries magnetic fields that extend far beyond the planets. And this outward flow forms a kind of protective bubble around the solar system that reduces the number of high-energy particles coming from outside. So when Voyager was still inside this region, the level of cosmic rays it detected was lower and more controlled, because the solar wind was constantly interacting with incoming particles and reducing their intensity before they could reach deeper into the system. As Voyager moved farther away from the Sun and approached the outer boundary of this protective bubble, the solar wind began to weaken, not suddenly but gradually over a long distance, and this weakening meant that its ability to block or deflect incoming high-energy particles also decreased, which allowed more cosmic rays from outside the solar system to pass through the region where the spacecraft was traveling. And when the instruments on board Voyager recorded this change, they showed a clear increase in cosmic ray intensity, rising by about 30 to 50% compared to levels measured inside the heliosphere, which was a strong and noticeable shift in the radiation environment. This increase did not happen as a single jump at one exact point, but instead appeared over a region of space where multiple changes were already taking place in particle density, magnetic field structure, and solar wind speed. So the cosmic ray surge became part of a broader transition where the protective influence of the Sun was no longer dominant, and the incoming galactic environment began to have a stronger effect on what the spacecraft was detecting. And this shift in radiation levels is one of the key pieces of evidence that Voyager was moving into interstellar space rather than remaining within the solar system's main influence. Inside the heliosphere, cosmic rays are partially blocked or slowed down by the solar wind, because the charged particles flowing outward from the Sun create a magnetic environment that deflects many incoming high-energy particles, and this effect acts like a large-scale filter that reduces the intensity of galactic radiation reaching the inner solar system. But this filter is not perfect and changes over time depending on solar activity, because when the Sun is more active, the solar wind becomes stronger and the shielding effect increases, while during quieter periods the shielding weakens slightly, allowing more cosmic rays to enter even inside the heliosphere. As Voyager moved beyond the main influence of this solar wind, the filtering effect weakened significantly, and more cosmic rays were able to pass through the outer regions without being deflected, which is why the spacecraft recorded a steady increase in high-energy particle counts. And this increase is not just a simple change in numbers, but a reflection of a fundamental shift in the environment, where the dominant control over particle movement is no longer coming from the Sun, but from the broader galactic environment, which allows cosmic rays from distant sources, such as supernova explosions and other energetic events in the galaxy, to reach the spacecraft more directly. The 30–50% increase in cosmic ray intensity recorded by Voyager is important because it shows that the boundary of the solar system is not a sharp cutoff where shielding suddenly ends, but instead a region where the shielding effect weakens over distance, allowing more external particles to gradually enter. And this gradual increase in cosmic radiation is one of the strongest indicators that the spacecraft has moved into a different plasma environment where galactic processes begin to dominate over solar processes. Cosmic rays themselves are extremely high-energy particles that travel through space at nearly the speed of light, and they come from a wide range of sources outside the solar system, including exploding stars, black hole activity, and other high-energy events in the galaxy. And when these particles enter the solar system, they interact with the solar wind and magnetic fields, which can reduce their intensity or change their direction. But once the influence of the solar wind becomes weaker near the outer boundary, these particles can move more freely, which leads to the increase detected by Voyager. This increase in cosmic rays is also important for understanding the radiation environment of deep space, because it shows that outside the protective influence of the heliosphere, space becomes more exposed to high-energy particles that are not significantly reduced by solar activity. And this has implications for any future spacecraft that travel beyond the solar system, because it means that radiation levels in interstellar space are higher and more constant compared to regions inside the heliosphere, where the solar wind provides partial shielding from these energetic particles. At the same time as this cosmic ray surge was being recorded, Voyager also provided information that helps explain why the edge of the solar system cannot be treated as a simple line or boundary, because the data shows that solar influence does not end suddenly at a single point. Instead, it fades gradually over a wide region where different physical processes overlap, including solar wind pressure, interstellar medium pressure, and the galactic magnetic field. And these three elements together shape the structure of the outer solar system in a way that creates a broad transition zone rather than a sharp edge. Solar wind pressure is one of the main forces shaping this region because it represents the continuous outward flow of charged particles from the Sun, and this flow carries energy and magnetic fields outward into space. But as it moves farther away from the Sun, it spreads out and loses strength. And this reduction in pressure means that its ability to maintain a strong, organized structure decreases over distance, leading to a gradual weakening of solar influence rather than an abrupt stop. Opposing this outward flow is the pressure from the interstellar medium, which consists of very thin gas, plasma, and magnetic fields that fill the space between stars. And even though this medium is extremely low in density compared to anything inside the solar system, it still exerts a form of pressure over large distances. And when this pressure interacts with the outward flow of the solar wind, it creates a balance region where neither side completely dominates. And this balance does not form a sharp line, but instead creates a wide zone where both influences are present at different strengths, depending on location. The galactic magnetic field adds another layer of structure to this region, because it extends across the entire Milky Way and influences the motion of charged particles over vast distances. And even though it is weak compared to magnetic fields near stars or planets, its large-scale presence means that it can affect how plasma behaves in the outer regions of the solar system, especially where the solar wind has weakened enough that external magnetic influence becomes more noticeable. And this interaction contributes to the gradual blending of solar and interstellar environments. When these three factors combine, solar wind pressure, interstellar medium pressure, and galactic magnetic fields, They create a region where no single force is dominant across all distances, and instead the environment changes gradually as these forces interact differently at different points in space, which is why Voyager's data shows a continuous shift in particle behavior, radiation levels, and magnetic structure, rather than a single sharp transition point. How far Voyager is actually going. Voyager's journey into the outer boundary of the solar system did not produce a single clean moment where every instrument agreed at the same time that a clear transition had been crossed. Instead, what happened was a long sequence of overlapping signals, partial measurements, missing data points, and indirect indicators that all had to be interpreted together in order to understand what region of space the spacecraft was actually moving through. And this is where scientific disagreement began, not because the data was wrong, but because the environment being measured was extremely complex, changing, and not easily described using simple boundary definitions. The main reason scientists debated Voyager 1's exit timing from the heliosphere comes from the fact that different instruments on board the spacecraft did not all show the same type of transition at the same time, because one set of instruments would show a clear drop in solar wind particles, while another set would still detect magnetic field structures that looked similar to those inside the heliosphere, and at the same time, cosmic ray levels were increasing, which suggested a move into interstellar space. But the magnetic field direction did not immediately match expectations for a fully interstellar environment, and this mismatch created uncertainty about whether Voyager had fully crossed the boundary or was still inside a mixed transition zone. This situation became even more complicated because the heliosphere itself does not end in a sharp line. Instead, it fades gradually over a large region where solar wind pressure weakens and interstellar medium pressure becomes stronger. And this means that there is no single measurement that can define the exact crossing point in a universal way, because different physical properties change at different rates and at different locations. So depending on which instrument is used as the primary indicator, the crossing point can appear slightly different in timing and interpretation. One of the biggest challenges in interpreting Voyager 1's data came from instrument calibration limits, because the spacecraft was built in the 1970s with technology designed for a mission lasting a few years near the outer planets, not decades of operation in interstellar space. And over time, as Voyager moved farther from the Sun and its environment became more extreme in terms of radiation exposure and particle variation, small uncertainties in instrument readings became more significant, especially when trying to measure very low density plasma conditions, where signals are weak and difficult to distinguish from background noise. The plasma instrument on Voyager 1 added another layer of difficulty because it stopped functioning properly early in the mission, which meant that direct measurements of plasma density in the outer heliosphere were no longer available from that instrument, and instead scientists had to rely on indirect measurements from other systems, such as the plasma wave subsystem, which detects waves in the surrounding plasma rather than measuring particle flow directly. And this shift from direct to indirect measurement created additional uncertainty because it required interpreting environmental conditions based on secondary signals rather than direct sampling of particles. This reliance on indirect measurements became especially important when Voyager approached the outer boundary, because the most direct way to measure plasma flow was no longer available. So scientists had to combine information from cosmic ray detectors, magnetometers, and plasma wave data to build a complete picture of the environment. And each of these instruments was measuring a different physical property, which meant that interpreting the overall region required connecting multiple independent signals that did not always change at exactly the same time or in exactly the same way. The cosmic ray data showed a clear increase in high-energy particles coming from outside the solar system, which strongly suggested that the spacecraft was moving beyond the main protective influence of the heliosphere, while the magnetometer data showed that the magnetic field was changing direction more gradually than expected, and the plasma wave data indicated variations in electron density that suggested a mixed environment rather than a clean separation between solar and interstellar space. And when all these readings were combined, they pointed toward a transition zone rather than a sharp boundary. But the exact point of crossing remained difficult to define with precision. This led to scientific discussion about what it actually means for a spacecraft to leave the solar system, because the definition depends on which physical property is used as the reference, whether it is plasma flow, magnetic field structure, or cosmic ray intensity. And since all of these change over different distances, the idea of a single exit point becomes less clear, replaced instead by a region where multiple transitions overlap. And Voyager's data sits inside this overlapping region, which makes interpretation complex, even though the overall trend is consistent with moving into interstellar space. Another source of debate came from the unexpected behaviour of the magnetic field near the boundary, because earlier models predicted that once Voyager crossed the heliopause, the magnetic field direction would shift more sharply to match the interstellar magnetic field. But instead, what was observed was a smoother transition, where the field outside the heliosphere appeared more aligned with the field inside than expected, which raised questions about whether the spacecraft had fully exited the solar magnetic influence or was still within a region where both solar and interstellar magnetic fields were interacting strongly. This magnetic alignment was one of the most surprising results, because it suggested that the transition between solar and interstellar space is not a simple break, but a gradual blending of magnetic structures over a wide region. And this finding contributed to the idea that Voyager may have been moving through a boundary layer where both environments coexist and influence each other rather than a single sharp interface separating them. The disagreement over timing also came from the fact that Voyager 1 and Voyager 2 crossed similar regions at different times and under different conditions, because they travelled in different directions through the heliosphere, and this meant that the structure of the boundary they encountered was not identical, since the heliosphere itself is not symmetrical but shaped by the motion of the Sun through the galaxy and variations in interstellar pressure. So each spacecraft provided a slightly different view of where and how the transition occurred. Voyager 2's later crossing in 2018 helped confirm some of the patterns seen by Voyager 1, including the increase in cosmic rays and the drop in solar wind particles. But it also showed differences in timing and magnetic field behaviour, reinforcing the idea that the heliopause is not a single uniform surface, but a complex and variable boundary that depends on direction and local interstellar conditions. As Voyager continues moving outward, it is no longer influenced strongly by the solar wind, but it is still within the broader environment of the Milky Way galaxy, where it travels through interstellar space that contains hydrogen plasma, cosmic dust, and weak but widespread magnetic fields that extend across large distances. And this environment is not empty or static, but filled with low-density matter and energy that continues to affect the spacecraft's measurements even far beyond the heliosphere. Voyager 1 is now moving through interstellar space, where the Sun's influence is very weak, but still detectable in some indirect ways, and its trajectory will continue carrying it through the galaxy for billions of years, unless it encounters something extremely unlikely, such as a direct collision with a dense object, but in normal conditions, it will simply drift through the Milky Way, gradually becoming more isolated from any strong gravitational or magnetic influence as time passes. Voyager 2 is also now in interstellar space, but followed a different path out of the heliosphere, which means its measurements provide a second perspective on how the boundary behaves in different directions, showing that the heliosphere is not uniform, but shaped like an uneven bubble that changes depending on how solar wind pressure interacts with surrounding interstellar material. And this difference between the two spacecraft helps build a more complete picture of the outer solar system structure. Why we got under 50,000 degrees Celsius headlines. The under 50,000 degrees Celsius headline came from a real measurement trend in Voyager data, but the way it was written and repeated in media turned a specific plasma physics reading into something that sounds like a physical temperature in the normal sense, like heat in air or fire, And that mismatch between what the data actually represents and how it was described is where most of the confusion begins, because in space physics, temperature does not mean what people usually expect it to mean, especially in regions where density is extremely low and particles behave more like individual fast-moving objects than a connected gas. In the region Voyager passed through near the outer heliosphere and into interstellar space, the instruments were not measuring heat in the way a thermometer measures temperature on Earth. Instead, they were measuring particle energy distributions, meaning how fast individual particles are moving and how much kinetic energy they carry. And when these values are converted into an equivalent temperature scale using physics equations, the result can produce extremely high numbers, like tens of thousands, or even over 100,000 Kelvin. But these numbers do not represent a hot environment in the way fire or boiling water does. They represent how energetic individual particles are in a very thin plasma, where collisions are extremely rare. The key reason this creates misunderstanding is because temperature in normal life depends on constant collisions between huge numbers of particles, where energy spreads evenly through contact and creates a stable heat level that can be felt. But in space at the edge of the solar system, the number of particles is so low that collisions almost do not happen at all, which means each particle moves mostly on its own, carrying its own energy without sharing it efficiently with others. So when instruments measure this motion, they detect high energy per particle even though there is no dense medium to transfer that energy as heat. And this is why a region can be described as extremely hot in data terms while still being physically cold in any practical sense. The confusion between temperature and particle energy distribution is one of the main reasons that the CI 50,000 degrees Celsius headline spread widely, because what the instruments actually measure is the spread of particle velocities, where some particles move slowly and others move extremely fast due to shock interactions, magnetic acceleration, and boundary compression effects. And when this spread is converted into a single temperature value for comparison, it produces a number that represents average kinetic energy rather than thermal heat. But when this is simplified for public communication, the distinction between energy per particle and heat in a dense gas often gets lost, leading to descriptions that sound like Voyager entered a region of extreme physical heat, which is not what the measurements actually show. Another layer of misunderstanding comes from how media reporting simplifies complex physics into single striking numbers, because space plasma environments involve multiple interacting variables including density, velocity, magnetic field strength, and radiation levels. And when all of these are reduced into a single headline figure, the result can easily become misleading, especially when the number is large and expressed in familiar temperature units like Celsius or Kelvin, which naturally suggest heat in the everyday sense rather than statistical energy in a low-density plasma. The actual region Voyager passed through is better understood as a zone where particle energy increases due to compression and magnetic interactions, where the solar wind slows down and transfers energy into individual particle motion, and where shock-like structures and magnetic reconnection events accelerate particles to very high speeds. And because the density is so low, these energetic particles do not transfer heat in the usual way, but still produce high readings when analysed through plasma physics equations, which is why the temperature value becomes so high, even though the environment would not feel hot to any object passing through it. If a human spacecraft were to enter this region, the first major factor it would encounter is not heat, but radiation. Because cosmic rays and high-energy particles from outside the solar system become more intense beyond the heliosphere, and these particles carry enough energy to damage biological tissue and electronic systems over time, especially during long exposure. And while the spacecraft itself would not be heated in the traditional sense, the radiation environment would be significantly more intense than inside the protective bubble of the solar wind, requiring strong shielding and careful mission design to protect both equipment and any potential human occupants. The second important factor is that despite the extremely high temperature values in plasma data, there is almost no actual heat transfer in the usual sense, because heat requires collisions between large numbers of particles. And in this region, the particle density is so low that even though individual particles may carry very high energy, they rarely collide with each other or with a spacecraft in a way that transfers significant thermal energy, meaning a spacecraft would not experience burning or heating like it would in an atmosphere or near a star. Instead, it would experience a sparse but high-energy particle environment where impacts are rare but potentially damaging over time due to their high individual energy. Electronics degradation risk becomes a serious concern in this type of environment because high-energy particles can pass through materials and disrupt electronic components by knocking electrons out of atoms, creating small but cumulative damage in circuits, sensors, and memory systems. And over long periods, this can lead to gradual degradation of performance or failure of sensitive systems, especially in deep space missions where repair is impossible and shielding is the only protection. So spacecraft designed for such environments must rely heavily on radiation-hardened components and redundant systems to maintain functionality over extended missions. Communication delay is another major factor that becomes extreme at these distances, because Voyager is already more than 15 billion miles from Earth, which means that radio signals travelling at the speed of light take over 20 hours to reach the spacecraft and another 20 hours to return, creating a one-way communication delay that makes real-time control impossible. And for a human spacecraft operating in this region, any system would have to function autonomously without immediate guidance from Earth, since even small adjustments would take nearly a day to be communicated and confirmed. The combination of high radiation exposure, low but high energy particle density, electronic vulnerability, and extreme communication delay creates an environment that is not dangerous because of heat, but because of isolation and energetic particle impact, where the main challenge is not surviving temperature in the normal sense, but maintaining system integrity in a region where energetic particles continuously pass through space with enough energy to cause damage over time, even though the surrounding environment remains extremely thin and does not behave like a hot gas or plasma in the conventional sense. The reason the Kulidaika's 50,000 degrees Celsius label persists is because it provides a simple way to express the unusually high kinetic energy of particles in this region, but without proper explanation, it becomes misleading, because it suggests a thermal environment that does not exist, while the actual physical situation is a low-density plasma, where energy is concentrated in fast-moving particles rather than in a dense, heat-carrying medium. And this difference is critical for understanding what Voyager actually measured as it moved through the outer boundary of the solar system and into interstellar space. What Voyager recorded is not a place of heat in the usual meaning, but a region where energy behaves differently due to low density, magnetic interactions, and shock compression, where particles carry extreme speeds, but do not transfer that energy efficiently through collisions, and where the main danger to any spacecraft is not burning or melting, but long-term exposure to radiation and energetic particle impacts, combined with extreme communication delays, and the need for fully autonomous operation in a region far beyond direct human control. What the edge really means scientifically. Voyager's data has become one of the most important sources of real information about the outer boundary of the solar system, not because it was originally designed for that purpose, but because it survived long enough to physically reach a region that no other spacecraft had ever entered before. And what it sent back changed how scientists understand the structure of space around the Sun. Because before Voyager, there were only models, simulations, and indirect observations from Earth-based instruments. But Voyager provided direct measurements from inside the region where solar influence ends and interstellar space begins. And that direct sampling is what makes its data unique even today. The first major importance of Voyager data is that it provides the first direct measurement of interstellar space conditions from inside that environment, meaning that instead of relying on distant observations or theoretical models, scientists were able to see actual readings of particle density, magnetic field structure, and cosmic ray intensity from a spacecraft physically located outside the heliosphere. And this allowed them to confirm that interstellar space is not empty, but filled with low-density plasma, cosmic rays, and weak magnetic fields that still have measurable structure and behavior over large distances. This direct measurement is especially important because it helps refine and correct models of the heliosphere itself. Since the heliosphere is not a fixed or perfectly symmetrical bubble, but a structure shaped by the balance between solar wind pressure and interstellar medium pressure, and before Voyager crossed this region, the exact shape, thickness, and behavior of this boundary were not fully known, because all models had to rely on indirect observations from inside the solar system. But Voyager's measurements showed that the boundary is more complex, more layered, and more dynamic than expected, with gradual transitions in particle density and magnetic field direction rather than a single sharp edge. Another major importance of Voyager data is its role in understanding cosmic ray shielding around Earth and the rest of the solar system, because the solar wind acts as a protective barrier that reduces the intensity of high-energy cosmic rays entering from the galaxy. And Voyager's measurements of how this shielding changes near the outer boundary help scientists understand how effective the heliosphere is at protecting the inner solar system, and how that protection changes depending on solar activity, distance from the Sun, and interaction with interstellar pressure. And this information is important not only for space science, but also for understanding radiation exposure risks for future deep space missions. Voyager also provides key data for mapping solar system boundary physics, because the region it traveled through includes multiple transition zones such as the termination shock, the heliosheath, and the heliopause. And each of these regions has different physical properties, including changes in particle speed, density, and magnetic field behavior. And by recording how these properties change over distance, Voyager allows scientists to build a layered map of how the solar wind slows down, compresses, and eventually merges with interstellar space, creating a clearer picture of how the solar system interacts with its galactic environment. As valuable as Voyager data is, the spacecraft itself is slowly reaching the end of its ability to communicate, because its power source is a radioisotope thermoelectric generator that produces electricity from the decay of plutonium. And this decay is gradual and irreversible, meaning that the available power decreases over time as the radioactive material loses energy. And as power drops, the spacecraft must shut down non-essential systems one by one to conserve energy for its most important instruments and communication systems, which allows it to continue operating, but with fewer capabilities as the years go on. This gradual power decline means that Voyager is expected to lose its ability to send signals back to Earth sometime in the 2030s or 2040s, depending on how long the remaining power can support the transmitters and scientific instruments. And once this happens, the spacecraft will continue traveling through interstellar space silently, still moving through the galaxy, but no longer able to communicate its position or measurements back to Earth, effectively becoming an uncontactable object that continues its journey without active connection to human observation. Even after it stops transmitting data, Voyager will continue moving through space for billions of years, because there is no significant force in interstellar space that will bring it to a stop or cause it to fall back toward the solar system, and instead it will drift through the Milky Way galaxy at its current velocity relative to the Sun, passing through regions of varying density and magnetic structure, but without any major interaction unless it happens to come close to a star system or dense cloud of material, which is extremely unlikely on human timescales. There are currently no planned missions that will travel as far as Voyager has reached, because the distances involved are so large that even with modern propulsion systems, reaching the outer heliosphere takes many years. And reaching interstellar space requires extremely long mission durations, high reliability systems, and carefully planned energy sources, which makes Voyager still the most distant human-made object in space, and likely to remain so for a long time. The final understanding of what the edge of the solar system really means comes directly from Voyager's data, which shows that there is no single physical wall or boundary marking the end of the Sun's influence. Instead, what exists is a dynamic plasma interaction zone, where solar wind flow, interstellar medium pressure, and galactic magnetic fields all interact continuously over large distances. And this interaction creates a shifting region where conditions change gradually rather than abruptly, meaning that the edge is not a line, but a broad transition area shaped by competing forces. This region is defined by the balance between solar plasma flow moving outward from the Sun and galactic medium conditions pushing inward from interstellar space, and neither of these systems completely stops at a single point. Instead, they overlap and adjust to each other over distance, creating layers where solar particles slowly decrease while interstellar particles slowly increase, and where magnetic fields from both systems interact and realign depending on local pressure and particle density. The idea of a hard boundary does not match the actual measurements because Voyager's instruments show continuous changes in particle density, radiation levels, and magnetic field direction rather than sudden jumps, which means that the heliosphere does not end in a sharp cutoff, but gradually fades into interstellar space. And this fading process creates a region where both solar and galactic influences are present at the same time, but in different strengths depending on location within the transition zone. The edge of the solar system is therefore best described as a plasma interaction region where multiple physical processes overlap, where solar wind loses strength and merges with interstellar medium where cosmic rays increase as shielding decreases, and where magnetic fields adjust to the balance of forces between two large-scale environments. And Voyager's journey through this region provides direct evidence that space at the boundary of the solar system is not empty, not static, and not sharply divided, but instead continuously shaped by the interaction between solar output and galactic structure over vast distances.